Hello and welcome to the Logos Research Associates live stream broadcast. I'm Zachary Klein, and it is my privilege to be your host for this presentation. For those new to these live streams, I'd like to briefly introduce the organization. Logos Research Associates is a community of scientists, scholars, and lay people that hold to a high view of science and of Scripture. The mission of Logos RA is to facilitate collaborative research within the creationist community, to recruit and mentor a new generation of Bible-believing scientists to continue the work, and to provide a clearinghouse for information that supports a biblical model of origins, and as we're going to see in tonight's presentation, information that challenges the evolutionary paradigm that dominates the scientific establishment. So before I introduce our speaker to begin our presentation, we'll open with a brief word of prayer, if you'd like to join me. Heavenly Father, we thank you for this opportunity that we have to come and to listen to this presentation from Dr. Fleming. I pray that it would be informative, that it would challenge, that it would edify all those who hear it, those who are listening live. We thank you for each of them. We thank you for those who will listen to the recording in days, weeks, months, even years to come. And I ask that all of these things would be done to your honor and glory. We pray this in Jesus' name. Amen. I now have the pleasure of introducing our speaker. Dr. Monte Fleming is a sedimentologist and geomorphologist with a focus on applied sedimentology. I'll let him explain those terms to you in the presentation. In a profession that depends heavily on field data, he is particularly interested in strengthening geologic models by integrating the field data with empirical findings from his research. Outside of the lab and classroom, Monte enjoys spending time with his 4 sons, directing vocal ensembles, and building cars. I'm going to have to ask about that one later. That sounds fascinating. His presentation tonight is entitled Dissenting from Deep Time, and this title comes from his book, actually. If you might put me back on the camera here for a second. I've got the book here by Dr. Fleming, Stories About Earth History, A Geologist's Descent from Deep Time. Fascinating book. Excellent resource. I'm sure Dr. Fleming will share more about it. We can talk more about it afterwards. Very much enjoyed that book myself. The presentation topic, the age of the Earth, can be scientifically measured and constrained in many ways. In this presentation, Dr. Fleming will share several of these methods for determining the Earth's age and talk about what they mean for the standard scientific paradigm. Dr. Fleming, can you hear me?
Yes.
All right. The time is yours, sir.
All right. Thank you. Let's see. So I was listening to a mathematician the other day, and she posted something. She has a large social media following, and she posted something, and she got a lot of about the age of the Earth, and she got a lot of replies back from Christians saying it's only 6,000 years old. And so she got on to reply to everyone, and she said, "Let me tell you why you're wrong." And she very respectfully and with a pretty good explanation, she started talking about this thing that I have here on the slide. Now, this is a picture that I took with an old cell phone several years ago through a microscope, but it shows something really fascinating. Let me get my laser pointer. And so there's a crystal right here in the center, and a few more little ones, and around each of these little crystals is a black hazy ring. Now that hazy ring is damage to the structure of the bigger crystal, the brown crystal, from radiation, and that came from uranium that was trapped in these small crystals that are zircons. That's biotite with zircons in it, and that those zircons had some uranium in them. And very slowly that uranium decays to lead. And if standard assumptions are correct, then it's very strong evidence that this crystal is very old. But as Zach read in the introduction, there are many ways to maybe test the age of the Earth. And some of them aren't going to give us straightforward answers, but they will at least constrain the age of the Earth. And some of those constraints are very interesting. So the answer about uranium and in the zircons, that is a very standard answer, and much of geology is based on that. That tends to be kind of a foundational. Not just that. There's also argon dating, potassium argon dating. There's rubidium strontium. Several of the types of dating that we use, but there are several natural phenomena that we can measure that could perhaps give us a different answer, and we'll look over some of those here. So the first one that we're going to look at is coastal erosion. And if you just ask Google, what is the erosion rate of the California coast? The answer you get back is about 0.2 meters per year. And if you ask the same thing for the East Coast, you get 2 to 3 feet per year. If you ask it how wide the United States is, it'll tell you it's about 300 miles, 3,000 miles, sorry. And so if we actually do the math on that, that only gives you a total time of about 5 million years for the coasts to erode into the center of the continent. Well, if we look at 5 million years compared to deep time, you can't even see the sliver. It's not even a thousandth of the graph. Now, to be clear about what we're talking about, get that laser pointer again. Now, here's a map of the United States from USGS, and you can see a blue, like a light blue continental shelf right here, and it's significantly wider on the East Coast. Now, remember that the erosion on the East Coast is faster than the erosion on the West Coast. And what's interesting is that if you measure this continental shelf and the erosion that's happened on it, and you extrapolate back, it looks like there are, well, doing a very rough Google Maps search, it looks like there's about 100,000 years of erosion on each coast. And of course, if conditions were catastrophic, that would happen much faster. Now, something that I should note before I move on is that this only works when the sea level is relatively constant. If the sea level drops significantly, it's going to push the ocean back out, and then it's going to have to erode its way back in. But even if that happens multiple times, we can see, looking at the coast, that millions of years have not passed. All right, what are some of the effects of coastal erosion? This is an island off of Greece, and you can see a cliff that's been eroded out by the ocean. That hill that's been cut by the ocean, it used to extend out significantly further. Here's a beach in France. And again, you can see that this used to just extend far off to the right, but it's been eroded back by the sea. This happened in Florida. This was a hurricane. You can even see the brick wall that used to be behind the house there. Another house that didn't suffer quite the same fate, but it's not doing very well either. Coastal erosion consumes about over 500 million in property each year in the U.S., and that's a value from many years ago. One interesting thing to note about coastal erosion is that there have been several lighthouses that have been preserved for history, just because they're historically significant. And what they have to do is, say they build a lighthouse 400 feet or so away from the ocean. Over 100 years, at 2 to 3 feet per year, most of the ground between the lighthouse and the ocean will erode away. And so in order to save the lighthouse, they have to move it. And this company, Expert House Movers, has moved 6 lighthouses. And when they move them back 300 or 400 feet, it gives them another 100 years as a tourist attraction. So the Southeast Lighthouse in Rhode Island, the Highland Lighthouse, Massachusetts, were a couple of good examples of that. Now, I would say that coastal erosion is completely consistent with biblical history. I would say that it is completely consistent with a global flood as recorded in Genesis. It's not consistent with typical geological processes forming most of the geologic column, because again, the amount of erosion that should have happened in a few tens of millions or a few hundreds of millions of years is simply not happened, and it's inconsistent with deep time. Let's look at basinal erosion. In other words, the erosion of the continents, the erosion that, like when rivers carry the continent out to the ocean. We can do a little bit of math and figure out the mass of Earth's land above sea level. And it turns out to be about 338 quadrillion tons. And a quick search will give a value of about 20 billion tons per year of sediment carried to the ocean annually. So if you divide one by the other, you get a total time of about 17 million years. And in that time, the current continents would be eroded flat. Now, some parts erode much more quickly than others, and well, some parts erode extremely fast, like the in Papua New Guinea, for example, is eroding much faster, and it would be eroded flat much more quickly. And some places don't have the river output to the ocean like other places do. But just as an average, now again, now it's a slightly bigger sliver, and it would be, well, that would be 4.5 billion years. And the continents, of course, nobody thinks that they've existed for that entire time. But you can see the problem here again. Here's some continental erosion, a canyon that's been cut by rainwater. Here is some grassland that has been eroded into by a stream, and it looks a lot like one of my favorite erosional events. This is Bryce Canyon in Utah. And I noticed something really interesting at Bryce Canyon several years ago when I was visiting. You can see this tree here, and the tree is standing up on its roots. The ground under it has eroded away. Now you can look down the slope and you can see that the erosion has not been consistent along the entire slope, fortunately, but that's a significant amount of erosion in just the life of that tree. A little better picture of the roots. The economic impact of soil erosion in the United States costs the nation about $37.6 billion each year in productivity losses. Damage from soil erosion worldwide is estimated to be about $400 billion per year. So again, I would say that this is completely compatible with biblical history. It's compatible with the flood. It's not compatible with typical geologic processes forming most of the geologic column or deep time. And what I would want to take a minute and talk about what people would say about this, what people on the other side would say about this. When it comes to coastal erosion, the typical answer is, well, it's complicated because you have the sea level going up and down. But even I've done some calculations with that, and even with all of that taken into account, there simply hasn't been enough erosion. With basinal erosion, that one is interesting. Typically, people would say that, well, the continents are renewed from underneath. Continents gain mass as more continental material is created. But we actually I don't think we have a really good model of how continents are created. So I would say, yeah, we don't really know how continents created, and if continents were being created from beneath for and being eroded off of the top, then we would expect the geologic column to disappear eventually, and that has not happened. So that's an interesting. I think that makes it clear that we haven't had all the cycles of erosion and then creating from underneath that we should happen if that is actually what's going on, if that's actually the explanation. Third thing I want to talk about is how big the deposits are in the geologic record. This is the Taphonomy sandstone, and you can see that it covers a vast portion of North America. And there are similar sandstones, a very similar sandstone on other continents as well. This sandstone was catastrophically deposited in many areas. I've seen pictures of car-sized boulders in the Taphonomy sandstone. So there was enough energy in the deposition of that sandstone to move boulders around. This is the Coconino sandstone. This, you can see it covers several states. This is the Morrison Formation and Chinle Group, again covering several states, and by comparison to the right, there's the Mississippi River deposits in the black line. You can see the difference between the ancient deposits and the modern deposit. I would say that that is completely compatible with biblical history, 6,000 years, about 6,000, give or take. Global flood is recorded in Genesis. It's not typical with geologic processes forming most of the geologic column, because when we look back, the further we look back down the geologic column, the processes are just wildly different from what we find in the modern world. I think when you really look at it objectively, you can see that. And the reason I say it would be compatible with deep time is because you could theoretically have a very large deposit, like you could have a flood many millions of years ago, and it could deposit something very big, and then you could have another flood a few million years after that, and it could deposit something very big. But it's easier to just have it all laid down more quickly for several of them, for several other reasons. Now, number 4, this is a really big one. Paraconformities is what we call them. They're missing layers. And what happens, how we end up with a missing layer, notice that there's a geologist here looking at an outcrop. And he's standing on one layer and he's looking at 3 more layers. There's another geologist standing in the same rock layers, but she's only got 2 layers where she is. And notice if you look at both of those together, the red sandy layer is missing on the right side. That's what's called a paraconformity. So somewhere in between those 2 outcrops, that red layer just went missing. It pinched out. And now between the second and third layer on the right side, there's a theoretical time gap, because that red layer, maybe it supposedly formed over a few million years. Well, now we should find a few million years of erosion in between those 2 layers on the right, but it's just not there. Let me show you some actual examples of this. So here's a gap that is supposed to be 6 million years of time. Now, the reason I took this picture in the center, get my pointer again, in the center, you can see what we call an injectite. And what this shows is that the sand from above, the lighter colored sand from above, actually got forcibly pushed down into the lower layer, into a crack in the lower layer. This is the Coconino sandstone and the Hermit Shale in the Grand Canyon. And again, there's supposed to be 6 million years of time in there, but there's no evidence of that time at all. This one, there's supposed to be 15 to 40 million years of time in here. This is the Moenkopi and the Shinnerup conglomerate. Moenkopi on the bottom, Shinnerup on top. And again, there is no evidence of the passage of time. And in fact, you can see that the lower layers were still soft mud when the coarser material of the shrimp was deposited on top. It's created these lode casts where the heavier stones have pressed down into the mud. This one is supposedly a gap of 50 million years, and this is between the sandstone and the Shinner conglomerate. But again, now there is a little bit of erosion at this contact, but not 50 million years worth of erosion. Remember that the entire, like the continents would be eroded away in 50 million years. Now this gap is supposed to be 155 million years. This is the Grand Canyon. But this happened in one night. This was a flash flood in Death Valley, and it created quite a bit of damage in just one little flash flood. But when you go back to these layers, you can't, there's very little evidence of erosion in those layers. This is definitely compatible with biblical history. This is one of the strongest arguments, geological arguments, that I know of for a short chronology. Definitely compatible with the global flood. It is not compatible with typical geological processes forming the geologic column or deep time. The reason I say it's not compatible with deep time is that if you compile all of these missing layers, and then shrink down the time to what actually looks like should have been there, then the vast bulk of the geologic column just collapses. The time that's in it, that is assumed for it, collapses. Another really interesting one is bioturbation. So bioturbation happens when an organism burrows through sediment layers and it disrupts it. So here we have a burrow. Here we have a burrow. You can see that these burrows are a couple of centimeters across. And then there are sediment layers around them. This is a burrow. I'm holding it upside down, but that's a nice helical burrow. This is what the sediment typically looks like. And this is Pisco Formation down in Peru. And you can see that it's not burrowed. This is here in North America, and again, it's just not burrowed. There aren't any burrows in that one. This is the Chinle Formation in Arizona. There aren't any burrows there either. That's the same. This is Navajo Sandstone. There aren't any burrows in it. So this is definitely compatible with biblical history. It's compatible with the global flood because you have one layer of mud or sand or rocks getting deposited quickly on top of another, and the animals just don't have time to make that many burrows. So it's not compatible with geologic processes forming most of the geologic column because in the modern world, sediments get burrowed very quickly. There are places in the ocean where it only takes a few hours to completely turn over new sediment layers. And even where I live in California, I ran an experiment several years ago where I dug a hole in my yard and laid down a few different colors of sand in layers. And then it rained, and 4 days later, the worms had churned up all those layers. Deep time, this is not really compatible with deep time either. Now, we can talk about the Pisco Formation. This is down in Peru. It's a fascinating area. It has thousands and thousands of whale fossils, penguins, cormorants, sharks, rays, just a plethora of amazing fossils. And it's down in this part of Peru. This is what it looks like. It's me sitting out on a sand dune. This was fantastic off-roading territory. It was very, very windy some days, and we were trying to protect our eyes from the flying sand, and we got creative here, and it worked. We got several more hours of work done that way. Here we are cleaning off a whale fossil. So what I found and what I did a research project on in this time was I found several whale fossils that were in cross-section in the cliff faces. So that allowed me to do a sedimentological analysis of the material around the whale fossils. Now, the one that you just saw, my interpretation of what happened is that the whale died, it landed on sediment. More sediment was deposited around it. A volcanic ash layer fell, slipped off the back. More sediment got piled on top of that, and then the whale decomposed, and the ash layer was left missing because we didn't find it over the whale. But this was the final structure of the sediment. So that means that material was deposited very quickly, and of course we can see that because it was not bioturbated. Here's another whale. You can see my backpack sitting off to the right and another bag off to the left. And those are whale bones just sticking out of the cliff face there. That's a close-up of it with the centimeter scale and an inch scale. You can see, I get my pointer again, you can see there is a vein here of gypsum running down on the left and another vein of gypsum running down the right of the whale. And on one side of that vein, the minerals from the whale's decomposition have not touched the sediment, and on the other you can see that there's black and red mineral that have leached out of the whale as the whale decomposed. So what we think happened on this one was, so the sediment there, this was actually in a trench, and so we think that got eroded out by the currents under the water. The whale rolled in and landed there and stayed there. More sediment got piled on top, and gypsum precipitated out of the water and stayed right there. And then the whale got compacted, and then some iron leached out of the whale. More gypsum was deposited to the right, and some manganese leached out of the whale, or I rather got attracted out of the seawater and stuck in the sediment. And that's the final state of the whale. So again, all of that material was deposited before the whale decomposed completely. Here's another whale. You can see a little better. You can actually see the ribs and the right front flipper, and the skull is off to the right. And you can see the channels that were eroded into the seafloor. The white is actually volcanic ash that fell onto the seafloor. It's pretty pure volcanic ash. So this was there's a lot of upheaval in this part of the ocean at this point in history. Now this whale was fascinating. This was not my research project. This happened before I got there. But they found baleen in one of the whale fossils, and they found it sitting on the flipper. So the baleen fell out of the mouth and landed on the flipper. And that happens over just a few hours or days, probably. And so it's not more than a few days before that happened. This whale died, and you can see the baleen in its mouth still. We call it the smiling whale. And again, baleen will fall out of a whale's mouth within days of death. So that means that this whale got buried very quickly. So in summary, we have rapid deposition of the sediment and the fossils. We don't have long breaks in the deposition, and we have very little bioturbation. And it's just one layer on top of another all the way through. So that is, I say, certainly compatible with biblical history. It's compatible with the global flood. In this case, it would appear to be near the end of the flood because it is a coastal deposit on the coast, but it's still quite catastrophic. And so it happened close to the modern coast. It's about 40 kilometers. And it does look like it used to be a marine environment, several indicators of that. It's not compatible with typical geological processes. This was clearly quite catastrophic, and there were an awful lot of volcanic ash and a lot of diatoms, and not compatible with deep time. Paleocurrents is a fascinating one. So when we see ripples in the fossil record, we can deduce the direction of the current that formed those ripples. And if we go through the geologic column, Precambrian, Paleozoic, Mesozoic, Cenozoic, Precambrian, if you kind of compile all of the data, well, I have a friend who compiled over 1 million data points, he and his students. And the data points that they compiled from the Precambrian, you can see that they're not terribly well organized. But in the Cambrian, they get much more organized. In the Pennsylvanian, they're also organized, but different direction. In the Upper Cretaceous, organized, but different direction still. And so, and then in the Cenozoic, the organization starts to disappear. So what that means is that you have currents that were somewhat coherent across the entire continent, and not just one continent. It was across multiple continents, starting about the Cambrian and going up into the Cenozoic. So that actually gives you a good, that gives us a good idea, a rough idea of when the flood started and when it ended in the geologic record. This is definitely compatible with biblical history. It's definitely compatible with the global flood. In fact, this is a very strong evidence that the global flood did happen. It's definitely not compatible with typical geological processes. And again, I say you could theoretically have a flood millions of years ago, and then another flood millions of years after that, and another flood millions of years after that, and that could create these currents. But that would require multiple global floods over tens and hundreds of millions of years. All right, biomolecules is a fascinating one. So we find biological molecules, including DNA, in many different organisms. And in fact, well, people didn't used to look for it because people just assumed that it wasn't there. But then people started finding it, and people started looking, and it turns out that you can find biological molecules in all kinds of fossils. We found DNA from a human that was supposed to be 45,000 years old, from a horse that was supposed to be 700,000, from a termite that was supposed to be 25 to 30 million, from a bee that was supposed to be 30 million, and many, many others. Now, this is problematic because a very careful study of DNA discovered that the half-life of mitochondrial DNA is about 521 years, and the half-life of nuclear DNA is about half of that, which means that in about 10 half-lives, you would not expect really to find any recognizable DNA sequences. And yet 1 million years is vastly longer than that. So you can see the problem. And it's not just DNA, as I mentioned. Here's a blood cell in a T-Rex. And it's not just molecules, it's actually living bacteria, which is just, they found bacteria in 34,000-year-old salt. I mean, they thought it was 34,000 years old. 500,000-year-old ice, 120 million-year-old salt, and 250 million-year-old salt. Now, that's not surprising to me because I think all of those are approximately 4,500 years old and not the tens of thousands to hundreds of millions. I don't think there's that much age difference in actual years between the 34,000-year-old salt and the 250 million-year-old salt. This is a problem, though, for long ages because radiation from the potassium in the salt damages the DNA and cellular machinery. And even dormant bacteria must maintain basic metabolic activity like DNA repair. And metabolic waste buildup will kill the bacteria in much less than 34,000 years, and certainly in 250 million. And just to give you a quick example, if so, 34,000 is 1.3% of 1% of 250 million. It's a tiny, tiny, tiny fraction of all of that time. And even the 34,000 years is a huge stretch for what a bacteria could survive. So something that has happened over this is that there's been quite a bit of debate in the scientific literature between people who say that they found this stuff, these biological molecules and these living bacteria, and people who say that's simply not possible. So therefore, your research is bad. So those debates have been kind of interesting, and I feel bad for the people that are doing good research and finding the stuff and getting criticized for their research from other people who have not done the research. Taphonomy means how fossils are created and preserved. It's very strange that we have fossils on Earth. The modern environment of the Earth does not produce fossils unless an animal falls into a cave or gets trapped in ice or gets stuck in tar or something like that. They have to be caught in a natural trap. And so it's very strange that we have all these mineralized fossils around in the geologic record. And there's an extraordinary break in the fossil record pre-Pleistocene. So Pleistocene is basically a pretty modern environment. Think of the mammoths and the giant sloths and the camels and lions in North America. That's the Pleistocene, and those animals are preserved in ice, tar, and caves. Whereas everything before the Pleistocene is preserved in waterborne sediment. So somehow, if you believe in the millions of years, then for hundreds of millions of years, everything was buried in waterborne sediment, and then all of a sudden in the Pleistocene, everything started being buried in a natural trap. That's just a very strange way. That is something very strange if that's true. It's much easier to posit a global flood where you get all the waterborne sediment preserving things, and it's rich with minerals. And then in the Pleistocene, you have more modern types of preservation. This is the Tar Pits Museum here in Los Angeles. A mammoth, a saber-toothed cat. Now this is from the Green River Formation in Wyoming. And if you look carefully, you can see that there's a small fish in the mouth of the big fish. You can see some bones sticking out here. Here's a palm tree in amongst some fish. So this got washed into the lake. This is a sloth, and apparently they like to swim, and this one got caught swimming. Here's a bat. They do not like to swim, but this one got caught in the same, well, this got caught in the lake as well. So this is definitely compatible with biblical history, global flood, and not with deep time. And I've included carbon-14 because in the beginning I mentioned uranium and potassium and rubidium and the other ways that they date rocks. And the point of including carbon-14 is to show that even in radiometric dating, there is a discrepancy. Some elements show that the Earth is old and others show that it is not old. So let's look at carbon-14. Carbon-14 is formed in the upper atmosphere, and then it decays, and the half-life is about 5,730 years. But we find it in coal, we find it in diamonds, we find it in dinosaur bones. So there are three options. It could be contamination, it could be measurement error, or it could be that the specimens simply aren't that old. Well, the people who do the laboratory work have tried very hard to get rid of the contamination. They've tried very hard to get rid of the measurement error. We cannot find a source of contamination in the ground that is nearly sufficient to explain the amount of carbon-14 that we find in the specimens. And so that leaves us with a very distinct possibility that the carbon-14 is original. It really looks like it's original. And so that means that the specimens simply aren't that old. And this is a graph that I put together with an equation that what this models, you can see the real age in years before present on the bottom, and on the side we have the expected carbon-14 age. And if there was not a lot of carbon-14 production in the environment before the global flood, this is what we would expect to see. And as it turns out, this actually matches reality fairly well. Carbon-14 is a little messy. Some years some years the Earth receives more radiation than others, and so that means that the input of carbon-14 into the environment is not 100% consistent. But what this means is that as you go back to about 3,000 years, 2,500, 3,000 years, the carbon-14 dates are quite good. As you get back to about 3,500 years, the carbon-14 dates start to deviate a little bit from the real date. And then by the time you get to 4,000 years before present, the carbon-14 dates are deviating significantly from the real date. So this is definitely, again, compatible with biblical history and a global flood, but not compatible with the standard model. So speaking of models, the standard scientific model, like why don't people know about all of these things? Now, I have seen a few things and a few comments in articles where people have noticed, for example, someone was doing work on the erosion on Mount Everest in the Himalaya ranges, and they noticed that the modern rate of erosion was far too fast. And so in the article, in the scientific article, they said erosion rates in the past must have been 50 times less than present. But they didn't have, of course, it's very difficult to imagine a mechanism that would actually slow erosion down by a factor of 50 times. People have done a lot of good work on how much sediment is put out by rivers, but they haven't done the math to figure out, well, what does that say about the age of the Earth, or what does that say about how fast the continent should be eroding? And certainly people have noticed paraconformities, but it's, even though it should be a really big deal, it's not taken that way in general. And so I'm taking now this quote: "It's beware of the sound of one hand clapping." That's a Zen Buddhist quote, and I'm misusing it. But what I mean is, when we're talking about science, people talk about, well, there is debate in the scientific community, and there is certainly debate in the scientific community. But from the spectrum of ideas that are out there, there's only debate allowed in a small percentage of those ideas. Nothing else is allowed. So it gives the illusion of debate, but the actual debate is stifled. Wait, for more, well, okay, so all of these things were from there's more evidence, more of this can be found in the book. I just gave a very quick overview and I skipped over some things. Thank you, Zach, for showing the book at the beginning. And I think I'm ready for some questions, if we have any questions.
Well, thank you, Dr. Fleming. This has been fascinating. We do have a few questions that have come in, and I'll get to them in a minute. And if folks have others, please go ahead and type those in, and we'll go through them. I guess there's a couple of things I'd like to. So, as I said at the beginning, I read the book and found it fascinating. And I think you talk about this in your book and in some other presentations you've given. This basic argument that there are geologic processes that aren't consistent with the radiometric ages, that's been around in creationist circles for a long time. What I appreciate about your book, especially when it comes to like erosion rates, that's actually kind of hard data to get. It's not always straightforward exactly how to calculate these things. So we actually have one question already that we'll get to that kind of relates to this. But maybe you could just share a little bit about kind of how that works when you talk about like coastal erosion, but then there's uplift, but then there's only so much erosion you can actually accommodate. So this question here actually relates to this. So yeah, I'll read the question. Some argue erosion rates cannot be used to accurately estimate the age of a continent because other geologic processes can mask reverse erosion, such as uplift or sediment deposition. So yeah, that's essentially the question. How do you compensate for all these complicating factors when it comes to the erosion of land masses in deep time?
So California is a good case study in the complexities of coastal erosion. So something fascinating about California, we have these in certain parts of the coast. We have these areas where the ocean has cut into the coast, and then relative to the sea level, the coast has come up. Now, it could be sea level dropping. It could be that we had an earthquake and it pushed the land up a little bit. And so we end up with several of these terraces, these marine terraces. But if you calculate the time that everything should have taken, it works for a few thousand years, and maybe you can even stretch it to a few tens of thousands in the past and make it work. But the erosion rate is just too much to accommodate into the current coastal structure, even with all of these other factors present. And then on the East Coast, it's more stable because it's not right up against this fault, and so the sea level has been relatively more stable over time. And so you would just again, there are marine terraces on the East Coast. They're harder to find, harder to see, but no, yeah, it's just even when you factor in all of those other things and try to make as nuanced an argument as possible, which I actually tried to do on one of Todd Wood's and Paul Garner's. I give a presentation for them on that specific topic. Even when you do all of that, it comes back that there's just simply not enough time there's the structure of the coast doesn't allow for much more time than maybe a few tens of thousands of years.
Yeah, I recall the podcast you talked about the continental slope, for example, and how the morphology, the shape of that shows that we couldn't have done these full cycles of uplift and erosion that you would need to accommodate. And that's what I think is interesting about your entire presentation is the strength of deep time. And for folks that are listening, hopefully we all know deep time is the idea that the Earth is millions to billions of years old. It's like deep space, deep time. The strength of deep time was that small processes over these long ages can do an incredible amount of geologic work. But that ends up being a problem for it because these processes actually are too quick when applied to these time scales. And when it comes to like our last question, there are processes that compensate, but it's like you're erasing the mark as you eventually you're going to run out of material to compensate, and you end up with a situation where the continent has to be uplifted, eroded down to nothing multiple times simply to last for the hundreds of millions of years that it's supposed to. Okay, so let's see. I think so. We have a couple more questions here that we can go through. This is a good one. This is from Sarah. I'll bring this up here. What are some tips for students to be able to discern between observations and interpretations of what they're taught when it comes to claims of deep time? How do you discern between the data and between the deep time interpretation of the data?
That is a great question, and I wish that every scientist were really good at this. It's very easy when you assume that your model is true to mix up data and interpretation. And so I would say just practice. Take an article and look it over carefully, and I think that just simply asking yourself that question, how do I tell between data interpretation in this article? Simply having that question in your head really helps.
Yeah,
because a lot of people they're not even asking it, and I think that's why they can fall into that trap.
Yeah, just looking for it is going to help. It's going to help you be a more critical reader. Yeah, that's a good take. Let's see. Got a question on the speed of light. I'm going to pass over that one for now. This is a good question. This actually goes back to your opening remarks. What is the creationist answer, the young Earth answer to the zircon radiation argument? You want to speak to that briefly?
That is a really, I wish we knew. I wish that reality were, well, it's, reality is very rich and complicated, and that's what makes science continually interesting, and that's what I think will make it interesting for forever. Because of our limited perspectives, all of the data do not always appear to point the same direction. I think we have really good evidence that there's something wrong with the uranium-lead dating, but I don't know what that is yet.
Yeah, the premise of your book and this presentation really is that there's a conflict, right? We've got the data pointing in two different directions. The geologic community has basically placed everything on radiometric dating methods,
right?
And yet there are other methods, plentiful examples, that don't line up. It doesn't make the radiometric clock go away. We still have to explain it, and that's still an ongoing problem and challenge. But there's a lot of other things that we can and should be looking at. So yeah, that's I think that's a good way to put it. It's a work in progress.
It is. I would add that it's something that's important to understand if you're really getting into this is how much of the geologic interpretations out there, and even genetic and paleoanthropological and all of these other scientific ways to all of these ways that scientists think of time, so much of it is actually based on uranium-lead dating, and they don't know that because it happened a long time ago and nobody's really thinking about it since then. But they're using that to calibrate everything, and so you can't so none of those other things like genetics are an actual independent argument for deep time. And when you actually look at genetics, it turns out to be a very strong argument for short chronology.
Yeah, it's interesting when you think about historically, right? There were early scientists that attempted to date the Earth by how long it would take to cool from a molten state or solidify liquids. And those arguments, those dating methods didn't pan out. Uranium lead, sorry, kind of stuck. And why is it that we assume now we've got the right clock after we've gone through a number potentials that ended up having to be abandoned, it certainly makes sense to at least be open to other
Yeah.
processes that can function as a dating scheme.
Yeah.
Let's see. Okay, this is an interesting one. Do you have any thoughts on the formation of goosenecks, entrenched meanders, like you see in southern Utah?
Yeah, that's a fascinating phenomenon. I would love to recreate that in a laboratory. I'm suspicious that what happened was that a normal meandering river formed, and then somehow, I wonder if there's a way that you can't pick up the flow at just the right rate so that it digs down into those meanders without destroying the meanders. Or if you maybe drop the end of the river, if that gets cut down, and maybe it can start cutting back through the meanders or something. I don't know. That's a really interesting geological problem. I'd love to tackle that.
Yeah, I've
I
seen
don't have
some
a
of
good
these.
answer though.
I've seen some of these in person, and what's fascinating to me is how every detail from if people aren't familiar with this, by the way, these things show up in screensavers a lot. They're really pretty. These
Yeah.
Horseshoe-shaped canyons is probably what people would recognize them as. But it's basically a meandering river that's been cut very, very deeply with very steep canyon walls. And what I've noticed when you look at these in person, every little diversion of the river at the bottom is reflected at the top. It's like a perfect, like even just in the past centuries, thousands of years, you would think you'd have some shortening and some significant change in the river direction. But it's a really, some of them anyways, are very pristine, very, very interesting. That's a great question, but yeah, that's something we need more work on. Let's see. Okay, this is okay. All right, so this is maybe a good general question we could kind of end on perhaps. How do scientists, so in general, reconcile differences between methods of dating Earth, like we've been discussing? What does this reveal about the reliability of our understanding of its age? How can we be sure if we have these conflicting approaches and conflicting clocks?
Well, what people do is mm, people tend to pick. I wouldn't say that the scientific community is not in general trying to be dishonest about this. What they're trying to do is take all of the data that they have at hand, and they're trying to fit it into the most coherent model that they can within the constraints of materialism. So now that last part, within the constraints of materialism, that's not spoken out loud very often, and most scientists don't even think about it that way, unless they, for whatever reason, unless they actually do debating or talking with people about this topic, which most don't. We just do our work. I would say that it would be very difficult to just approach the Earth with no ideas. Like, imagine showing up on an alien planet and trying to do geology, and the actual geologic history of the planet is vastly more complicated than you think it should be. And you're trying to sort out all that complexity. And I think the geologic history of Earth is equally as, like, the actual geologic history of Earth is extremely complicated. And so it's very difficult to just approach geology with a completely open mind and no preconceived ideas and figure out what on earth is going on. People needed and so people have had different starting points. I mean, first off, just because each of us is just one person and we can only do a limited amount of research in our lifetimes. So it's like, what does it say about reliability? Well, something interesting happened. Maybe this is a good analogy. Something interesting happened with James Webb Space Telescope. which is that a lot of people had to grapple with some data that actually, I read the data back in the 90s. I saw it in articles, but the James Webb telescope was so much better that it made it so that people couldn't ignore the data. And what I mean specifically is that they were finding heavy elements out at the edge of the visible universe. And the problem with that is that heavy elements theoretically come from supernova, or stars that are very close to supernova. So what that means is that you have to have a full life cycle of a star going on before you get heavy elements. And so if we're looking out to the very beginning of the universe, then we should not find heavy elements. We should only find the ones that were created by the Big Bang. Well, as soon as all that data from James Webb came back, people started immediately adding billions and billions of years to the age of the universe. What's a few billion years among friends? It wasn't, and so it's not that the model is good. It's just that that's what everybody has kind of settled on, and it's not that it couldn't get completely upset by new data. It's something that I appreciate very much about the biblical model is that once you get into, well, I mean, the Bible is it's a fascinating book, and it has a coherence that is utterly, it's remarkable. The coherence of the Bible is remarkable. And people will say, well, it's not a scientific textbook, and it's like, well, no, but it is a history book, and it has a lot of useful history in it, and so so I use it as a scientific tool, and I found it to be very helpful, where I can say, okay, this thing that I'm dealing with scientifically, this is what the Bible indicates maybe happened here, and then I can see if that actually pans out, and I can also use the standard model that I'm very familiar with and see how that how that might influence my interpretation if I, and just see what actually works. It's it's nice to be able to just ask questions, and not be artificially confined to a model that you have to protect at all costs. Now, I'm not worried that my research is going to destroy my faith, or and I suppose the reason is that I've seen over and over again that even when we find things that really look like challenges, if we work on it enough, we will come to a very coherent picture, and that picture will actually support the Bible. Over and over again, I've seen that. The Yellowstone fossil forest is a fascinating example of that, if people want to do some research. And so once you see that happen over and over and over again, you don't have to be concerned about the next rock you're going to kick over. And also, and it's not just science, of course. The whole goal is the relationship that we have with our Creator. And again, like when you've gone on that journey for a long ways, you don't have to worry that the next thing that you run into is going to shake it. It's a nice way to do that.
Yeah, that's well said. That as you were sharing that at the end, it reminded me of the words of Samuel in 1 Samuel 7:12, where he sets up the stone and says, "Hitherto the Lord has helped us." And we get to look back and see things that looked like insurmountable challenges, and good answers came for many of those.
Yeah.
And there'll be more challenges, it's guaranteed. And we won't solve all of them, but that's no reason to lose heart. That's great. All right. Well, our time is about up. Thank you, Dr. Fleming, for this presentation. This has been fascinating. I personally enjoyed it. I know that our viewers did as well. I'm going to bring up the information for next month. Next month's presentation, Wednesday, October 8th, same time. Our speaker will be Dr. Jeff Tompkins from ICR, and his topic is chromosome 2 fusion, which is a fascinating and controversial topic, even among creationists. So please do make plans to join us for that. It'll be a good conversation, a good presentation. And with that, I think we're going to go ahead and wrap this up. I don't think I have any other material to go through. Oh, yes, please do visit our website and our social media pages for Logos Research Associates. On our website, you can learn more information about the organization. You can also learn about some of the research projects that are currently underway, as well as some mentorship opportunities that are available for students and for people with various technical expertise that would like to be involved in research. So please do check out our website. Our YouTube channel will be the home for this recording and for other video content that the associates put out. So please do check out the YouTube channel as well. And with that, I'm going to close it in a brief word of prayer, and then we will wrap this up. So please join me. Heavenly Father, we thank you again for this opportunity to hear this fascinating information. We thank you for Dr. Fleming's research and for just the confirmation that your word is reliable, that science is indeed possible because you are a faithful and unchanging God that upholds the universe in a way that we can understand, that you have equipped us and even commissioned us to understand your creation. And we thank you for the work of Dr. Fleming and others who have gone on and done that. And I pray that this would be an encouragement, that it would edify and instruct everyone who hears. We pray all of these things in Jesus' name. Amen.